Hi guys, and welcome to this virtual lecture course on the quantum theory of condensed matter physics. I'm Dr. Andrew Mitchell, and in this lecture I want to talk about systems of interacting fermions. In the previous lectures, we talked about tight binding models, which are so-called quadratic Hamiltonians. They described a wide range of physics, from simple molecular systems to fermionic lattice problems. They described electrons with a potential energy background, plus also kinetic energy for quantum tunneling of electrons between different atomic orbitals. However, fundamentally, the electrons were not interacting with each other, and we could understand the physics of these problems in terms of the single particle energies and single particle states. We saw how, for example, we can do a simple Fourier transform of the Hamiltonian operator to bring it into a diagonal form for many periodic lattice structures, and understands the physics in terms of a simple band structure. For truly interacting problems, where the electrons see each other through the Coulomb interaction, this is not possible, and we need to resort to much more sophisticated techniques to understand the underlying physics. What are the underlying physics? Well, for example, it's possible to have an interaction-driven transition between a metal and an insulator, the so-called Mott transition. We'll discuss certain models of interacting fermions on the lattice, in particular the so-called Hubbard model, which treats the Coulomb interaction as very short range. It assumes that the interaction is dominant when you have electrons of opposite spin occupying the same orbital, in which case you have a strong repulsion. Otherwise, the electrons do not interact with each other at longer ranges. Although simplified, we'll see that this model is highly complex, but captures a wide range of physics, including the Mott transition. We'll also see how in this model, through a simple mean field approximation, we can understand the concept and the phenomenon of itinerant ferromagnetism, which is to say a metallic system that is also ferromagnetically ordered. This is basically the Stoner model of ferromagnetism. We'll also see, through a simple perturbative approach to second order in the quantum tunneling between atomic orbitals on neighboring sites, how we can derive the Heisenberg spin model from the more microscopic Hubbard model. Okay, let's get down to work.
Before we discuss the role of interactions in quantum condensed matter systems, I want to touch on the notion of electron spin. Of course, we know that electrons have spin. They are spin half particles. They are fermions. The spin is an intrinsic and fundamental part of the nature of these particles. However, in the treatments of the fermionic systems that we've discussed so far, spin has not been included. It has not needed to be included. However, there are many areas of physics where we do need to include electron spin. For example, if we want to describe magnetism, obviously we need to include electron spin. If we can have ferromagnetic ordering or antiferromagnetic ordering, this is something to do with the alignments of the electron spins, so we need to include spin in order to be able to describe the entire phenomenon of magnetism in materials. Also, if we have materials that involve the heavier elements, the coupling between the spin and the orbital angular momentum can be significant, and so to capture the effects of spin-orbit coupling, which can have dramatic effects, and this has been something that's been discussed in the literature recently in the context of topological quantum matter, if we want to describe spin-orbit coupling, we need to think about electron spin. Also, real materials, of course, have some amount of disorder at finite temperature, and they arise inevitably in any system. And if those impurities are, for example, transition metal atoms or some other kind of element with a localized moment, then we can have the phenomenon of spin flip scattering, which can dramatically change the properties of materials. Other areas in which we need to include electron spin, there are many, but one important example would be in superconductors. If we have a Cooper pair of two electrons of opposite spin, they can form a spin zero bosonic state, and then those Cooper pairs can condense into a superconductor. So to describe superconductivity, again, we need to think about electron spin. And of course, there are many, many examples where we need to think about electron spin. One important area which I want to talk about in this lecture is the short-range part of the Coulomb interaction between electrons in solids. So the Coulomb interaction, of course, is the electrostatic interaction between two negatively charged electrons in a material, which dies off as the inverse square of the distance. But of course, when one gets onto the nanoscale and thinks about electrons in atomic orbitals and moving around on a crystal lattice, then two electrons can only occupy the same quantum orbital if they have different spin by the Pauli principle. And so the dominant part of the Coulomb interaction is when the electrons are very, very close to each other because of the inverse square law, and that can only happen when the electrons occupy the same atomic orbital and they are of opposite spin. So to describe the most dominant part of the Coulomb interaction in solids, we need to take account of the electron spin. And that's actually something that I want to talk about in today's lecture. In particular, we'll see that if you only retain the local, shortest range part of the Coulomb interaction, which is the interaction between opposite spins in the same quantum orbitals, we can account for a vast range of physical effects to do with interactions between electrons. Often one doesn't need to include the long-range Coulomb interaction to capture the essential physics, and partly that's because of the screening of the interaction due to quasi-particles in the material itself. We'll talk about that a bit more later. So far we've treated fermions and electrons in particular in solids, but we have not discussed the role of spin. And in fact, we can simply regard spin as another quantum number to label our states. So, for example, with the electrons, we can use the label sigma to describe either up or down electronic spin states. And we just regard these as a different quantum number. We regard states with different spin as being different states or different orbitals. So, for example, we can write down second quantized fermionic operators for a site I with spin sigma. So Ci sigma dagger and Ci sigma. And these things act on the local Hilbert space which is simply either 0 or 1 for a particular quantum orbital labelled by the full set of quantum numbers I sigma. So Ci sigma dagger and Ci sigma act on a quantum orbital I sigma. So we just carry this extra label, and everything else is exactly the same about the algebra. We just regard the different sigmas as different orbitals. For example, if I want to create an electron in the orbital I sigma with my Ci sigma dagger, I can do that. It creates an electron in that orbital. Likewise, if I destroy an electron in an occupied orbital, I get the unoccupied orbital. And to complete the set, if I try to destroy an electron in a state that's already empty, I get 0. And by the Pauli principle, if I try to create an electron in a state that's already occupied, I get 0. From these, as before, we can write down the fermionic anti-commutation relations, but now I'll include the spin label. I can write down Ci sigma and Cj sigma primed dagger. The anti-commutation relations for these would be delta ij. We get 0 unless we're talking about the same quantum orbital, which means I has got to equal j. But we also need the spins to be the same, because it has to be the same quantum orbital. And so I also get delta sigma sigma primed. And similarly, I can write down the other anti-commutation relations. Two destruction operators have an anti-commutator which is 0, and two creation operators have an anti-commutation relation which is equal to 0. The non-trivial one of this list, of course, is this first one, where we consider a creation operator and a destruction operator, which is equal to 1 if we have both the same quantum orbital in terms of the index ij, and the same quantum orbital in terms of the spin sigma sigma primed. So everything else is really the same. We can sort of copy our whole system, if you like, for one spin, sigma equals up, and for the other spin, sigma equals down. So we can write down, for example, tight binding models which also carry this spin label. We can imagine a tight binding model of this generic form, which is of course quadratic, and here I've just included also the spin label sigma equals up or down. So the way it's written here, the spin label is completely passive. It's we just have one copy of the whole tight binding model for spin up, another one for spin down, and they don't talk to each other. However, we could imagine, for example, adding in here a sigma dependence to these parameters t, I, j, in which case we could imagine a tunneling of electrons from site I to site j that depends on the spin. And if we look at the diagonal elements, tii, sigma, they correspond to the single particle energies. If they are different for up and down spin, that's equivalent to a local magnetic field acting on that site, which of course then lifts the degeneracy between up and down spin. So this is a totally generic kind of quadratic tight binding model where we've included spin, and you see that really not much has changed. Indeed, I can diagonalize this system in principle and obtain something where I have just this sum over momentum k and the sum over spin of some single particle levels epsilon k, and let's carry also the label sigma here in general, and then ck sigma dagger ck sigma. So here we just have two bands, one for sigma equals up, one for sigma equals down. We could also imagine a kind of scenario where we have spin-orbit coupling. So let me write a spin-orbit coupling type of Hamiltonian. Again, let's be totally general. Imagine that we had a quadratic Hamiltonian involving real space sites I and j, and let's say we now consider the spin sigma on site I and sigma primed on site j. Either of those can either be up or down. Then in a totally general model, we'd have t, I, j, a parameter telling us about the tunneling from I to j, or it could be the on-site energy if I is equal to j. But then we also need to describe both the spin of one orbital and of the other orbital. So now we have four parameters, t, I, j, sigma, sigma primes. And such a Hamiltonian describing spin-orbit coupling in its most general form could arise, for example, if I have orbitals with orbital angular momentum L and spin sigma, and the thing that's conserved is the overall angular momentum, which is the orbital angular momentum plus the spin of the electrons, and therefore this would constitute a spin-orbit coupling. And we'd need to know not just the orbital I and j, which tells us about the angular momentum of orbitals I and j, but also the actual electron spin of particles in those orbitals. So this would be a more generic Hamiltonian, and what we'd see here is that because of the structure of this Hamiltonian, the overall spin is now no longer conserved. And when I diagonalize this Hamiltonian, then I can no longer write things by a momentum index alone, and instead I would sum over some label L and now the orbital and spins all get mixed up into a single label L, and I sum over all of these things for the single particle energies. So these are the different kind of things that can happen in quadratic type binding models with spin. It's really not so different from what we had before. Instead, all we have to do is imagine that the spin is just another quantum number which distinguishes different orbitals, maybe with the same real space position but with different spin. In terms of the algebra that we need to be able to compute things using this representation, things are not really so different. So if we use the representation of quantum orbitals involving spin, we see that, for example, we can write down a particular orbital I could have 0 electrons in it, it could have 1 electron in it, which could either be up or down spin, or it could have 2 electrons in it, which would then therefore have to be spin paired. So a single fermionic orbital actually has a local 4-dimensional Hilbert space. As opposed to the qubit states, which are just empty or occupied, 0 or 1. However, this is really the same as what we had before. It's really very, very similar. This state psi I that I've written down here, which is one of those 4 states, this really just means how many electrons are there inside I with up, and how many electrons are there inside I with down in the occupation number basis. And this just means, let's think of 2 distinct quantum orbitals, one for I up, and then we have the direct product with the vector space for I down. So this is really what these 4 states of our local Hilbert space actually mean. We can just write them in terms of the occupation number basis, and we just regard the up and down as different quantum orbitals. In particular, we can suppose that the empty state of site I is equivalent to the vacuum state of that site. We can also act with Ci up dagger on this empty state and get the up state on I, or I can act with Ci down dagger on the empty vacuum state and get the down state in state I, in site I. The interesting thing, of course, comes when I act with Ci up dagger and Ci down dagger, in which case I get, by definition now, the doubly occupied state. And remember that the order of those operators matters because they're fermions and they anticommute, and therefore I can write that Ci down dagger, Ci up dagger, swapping the order of those operators. We know from the anti-commutation relations, and indeed the basic property of the wave function antisymmetry for fermions, is that this will give us minus Ci up dagger, Ci down dagger acting on the vacuum, which is of course minus the doubly occupied state acting on site I. So again, we can be careful to construct our full Hilbert space and the operators which act on that Hilbert space. So you see that by introducing the spin, there's no real formal difference in the machinery that we've already set up. So what I want to do now is actually consider a wider and more general type of model that allows for interactions between electrons of different spins. And so we will consider electronic interactions in models of a very general type. This is still not the most general type that you could possibly write down, but it's still a very general type. The Hamiltonian would consist of the sum of two terms. One is the usual type-binding model. So this is a quadratic Hamiltonian. It's quadratic in the fermionic operators. Which are the set of Ci sigma operators and the Ci sigma dagger operators. And this is basically a type-binding model with spin included. And to this type-binding model, we now add an extra piece for the interaction. So this is the interaction between electrons, which is coming from the Coulomb interaction, which of course we know to be microscopically in the mix. And this is not a quadratic term in the Hamiltonian, but rather a quartic term. It's a 4 fermion term. So no cubic or linear terms or 5 fermion terms or things like that can ever appear in the Hamiltonian because the Hamiltonian conserves charge. So a Ci sigma dagger cannot exist in the Hamiltonian on its own because that would create a charge out of nothing, and that's not allowed. Likewise, if we had something like Ci up dagger, Ci up, Cj down, that would be a 3 fermion term, and again, overall, that destroys a unit of charge, which we don't allow in our models. So we only allow even numbers of operators. 0 operators is, of course, totally boring, nothing happens. We spent a good while looking at type-binding models, which are quadratic in fermionic operators, but to understand the role of electron interactions, we need to use 4 fermion terms. And we'll see that these are basically density interactions. The interaction between 2 electrons is of the type that I need to know whether an electron over here in orbital I is there or not, and electron here in orbital J is there or not, to determine whether there's an interaction or not. So I need to know simultaneously where 2 electrons are, so I need 2 different number operators, and each number operator consists of 2 fermions. Of course, most general kind of model you could write down could include even higher order terms, 6 fermion terms, 8 fermion terms, and so on. However, for virtually all of the kind of physics that we're interested in, 4 fermion terms would suffice. So what is the most general form of our interaction Hamiltonian if we allow it to be a quartic type term? Well, we have 4 fermions, so we'll have to have a sum over I, J, K, and L for our 4 different sites, and those orbitals can have different spins, which I'll call sigma 1, sigma 2, sigma 3, and sigma 4. Each of those sigmas can be either up or down spin. There will be some parameter, u, which tells us the strength of this interaction. It will depend on all of these things, which of course is an enormous tensor object with 8 indices, and the whole thing's horrific. And then I have the actual operators in question, which would be Ci sigma 1 dagger, Cj sigma 2, Ck sigma 3 dagger, Cl sigma 4. And of course I need 2 daggered operators and 2 not daggered operators. so that we overall conserve charge. And this is the most general thing that I could write down, with a sum over I, j, k, and L, and a sum over sigma 1, sigma 2, sigma 3, sigma 4. And the actual interaction is something that is parameterized, of course, by this tensor U. We can write down this interaction term in a diagrammatic form. We could imagine a particle J coming in. This particle J has spin sigma 2. Then it has an interaction and turns into a particle I with spin sigma 1. And it does that due to the interaction, which is denoted by this wiggly line. And that transformation of J sigma 2 to I sigma 1 happens due to the presence of another fermionic species, namely L sigma 4, which due to this interaction turns into a species K sigma 3. And this wiggly line is precisely this interaction U, which carries with it a dependence on all of these labels. And actually you can see already from this kind of diagram that if we have a total spin conservation in the system, then there should be some rule for this, and some of those matrix elements U in there will actually be 0 unless the total spin is conserved. And so what we can read from this diagram is that for this diagram to be non-zero, we require sigma 2 plus sigma 4 to be equal to sigma 1 plus sigma 3 if we have overall spin conservation. The charge conservation is already sort of guaranteed and taken care of through the fact that we have two destruction operators. They're the lines here that are heading in, and two creation operators, and they're the lines that are heading out. So we can describe these kind of things very nicely just in terms of these kind of diagrams. If we were to consider a general quadratic term by contrast, so for example in this tight binding model up here, let's imagine, let me just write this down again for sake of completeness. Here I just have terms ij between sites I and j. It's a two fermion term. Those things that I've written down there in blue for the tight binding model, we just have a single site. I should add in the spin labels here as well, shouldn't I? Let's write sigma 1 and sigma 2 in the mix. So I have a state coming in with labelled by orbital index j and spin sigma 2. And it gets transformed and flows out again from this term in the Hamiltonian, into a state I with spin sigma 1. And that is caused by this term in the Hamiltonian parameterized by Tij, and we can denote that by this sort of scattering event, as it's called, off this object, which is of amplitude Tij. This is the case where the scattering from a state j into a state I doesn't depend on the spin. But again, we have a spin conservation rule which applies at the vertex. Again, charge conservation was taken care of because we have one inward going line to the vertex and one outgoing line, spin conservation just requires, in this particular case, sigma 1 is equal to sigma 2. In the 4 fermion case, it's a bit more complicated. There are actually many different possibilities, because sigma 2 plus sigma 4 could equal sigma 1 plus sigma 3. So there's a wider range of possibilities for the 4 fermion term, the interaction term. So often it's nice to think about these kind of terms in Hamiltonian diagrammatically in this way. The quadratic terms as kind of scattering events, and these interaction terms as these sort of pairwise interactions between ingoing and outgoing particles. And for the interaction terms, the microscopic origin of the interaction between the electrons is, of course, the Coulomb interaction, which is actually a pairwise interaction between particles. So here we're not going to consider fundamental 3-particle interactions or 4-particle interactions and so on. Of course, there may be effective or emergent higher-order interactions coming out from the simple Coulomb law, but the microscopic law that we put into our models is just going to be this pairwise interaction. And as it turns out, the dominant interactions are so-called density-density interactions. They basically depend on the number of electrons in a particular orbital and the number of electrons in a different orbital, and also their spin. So we will take a specific form of the most general interaction term and write it just as the sum over site or orbital indices I and j, and then the spin of electrons in those orbitals sigma 1 and sigma 2. And we'll just write down a tensor object which involves these 4 indices. And we count the number of electrons in orbital 1. That's like the density, if you like, of electrons in orbital number 1 with spin sigma 1. And then we count the number of electrons in orbital j with spin sigma 2. And we have the product of these two terms. So this is a specific form of the most general kind of interaction that we considered on the previous slide. This is obviously not quite the most general kind of thing that we can imagine, but it's a density interaction, and it's the dominant part of the full interaction. And of course, we can write that in terms of the number operators. These combinations Ci sigma 1 dagger Ci sigma 1, that's obviously the number of electrons in orbital I sigma 1, and Cj sigma 2 dagger Cj sigma 2 is the number of electrons in orbital j sigma 2. And in particular, for the Coulomb law, or the Coulomb interaction, let's call it, we have that Uij goes as E squared, where E is the charge of the electron, over 4 pi epsilon with some permittivity epsilon, divided by the separation in real space of the two sites. So it depends on the distance between the two sites. So if site I is located at position Ri on the lattice and orbital j is located at position Rj, then the vector and difference Ri minus Rj, if I take the length of that vector, that's the real space difference between those two sites. And we know that the potential energy due to the Coulomb force goes as 1 over this distance. And of course, it's the energy that we're writing here in the Hamiltonian rather than the electric field or the force or something like that, which would be 1 over r squared. And you can see, of course, from this expression that this requires that I not be equal to j, because otherwise we'd be talking about the same site, and then downstairs we'd have 0, and we don't want to be dividing by 0. So this that I've written down here, this Coulomb interaction, is a so-called long-range interaction. It's something that actually goes out to infinity. There's always a finite interaction between any two electrons, wherever they are in the universe. It might become very, very small because of this 1 over distance formed to this potential, but is there in principle. But that's actually not the only kind of interaction that exists, because we also have a very much stronger kind of interaction between electrons that exist in the same quantum orbital. Okay, so here we have to be a bit more careful. We know from the Pauli principle that two electrons cannot occupy simultaneously the same quantum orbital with all of the same quantum numbers, but they can exist in the same quantum orbital, let's say, if they have different spin, because the spin is also a quantum number. So if I have different spin, then two electrons can occupy the same quantum orbital. And that means that their position, if you like, the orbital index, I and j, that they can be equal, provided that the spins are opposite. And this is not accounted for in this equation that I've written down, and so there's a short-range piece that we can also include. And this local interaction is actually the dominant term that we have to consider most of the time, and this is called the Hubbard interaction. And this is short range. It's really short range, it's just local, in fact. So if you write down this Hubbard term in our Hamiltonian, this is now diagonal in the site index, because we're considering just a local effect. Our enormous 8-index interaction tensor now just becomes a sort of vector, if you like, with a single index in site space. And then the actual operators in the Hamiltonian for a given site I involve the interaction between the up and the down electrons on that site. And we can write that, of course, in terms of creation and destruction operators, and it's just a 4-fermion term. Ci up, dagger, Ci up, Ci down, dagger, Ci down. And we can see from this expression that the interaction energy is only non-zero if there's a double occupation of a particular quantum orbital with oppositely paired spins. So we only get a contribution to the energy if the site is doubly occupied. But of course, to be able to compute whether or not a site is doubly occupied, we can't use the single particle states that we were talking about in the previous lecture. We need to consider the many particle states because we need to know simultaneously what's happening to multiple electrons. So when analysing interacting systems, we are not going to be able to simply work with the product of single particle states. So in this course, we'll consider interacting fermion systems using the so-called Hubbard model. There are, of course, more general models that one could write down, but as I've just motivated, this actually contains the most dominant features, and actually this model is incredibly rich and captures a very wide range of physics. It's actually an open question as to the kind of physics that are contained in Hubbard models on different lattices, and this is still very much a field of active research right to the present day. There are no exact solutions to this model, as we'll see, except in very specific circumstances, and so one has to really use ingenuity to find out the physics of these kind of systems. So the Hubbard model basically consists of a tight binding model on some given lattice with some local on-site Coulomb interactions. So if we have a model that respects charge conservation and also spin conservation, then the Hubbard model would take this form. We have in the first term a tight binding model where the Tij's actually define the dimensionality and geometry of the lattice, and then we have this interaction term. In fact, we'll actually make another simplification. This is a physically motivated simplification. We'll consider lattice systems with a periodicity where the interaction is not going to change from site to site. We have a repeating unit on the lattice where going from one unit cell to the next, we have identical physics, and therefore we don't have an inhomogeneous interaction ui, we have a constant u for all sites. Furthermore, we can consider the dominant quantum tunneling between orbitals to be short-ranged. We know that the overlap between atomic orbitals, of course, is exponentially decaying with distance, so we can just consider, for example, nearest neighbor interactions on the lattice rather than a quantum tunneling between orbitals that are rather distant, and therefore we can make a simplified version even of this model, which will involve the sum over sites I and j, which are nearest neighbors, and the fact that they're nearest neighbors is denoted here by these angle brackets, as usual. We'll have a sum over spins, sigma, which are either up or down. And then we'll have the usual terms for our tight binding model, and we'll just say that these are all equal to each other for nearest neighbors on the lattice. And I'll write out explicitly the Hermitian conjugate terms here. And then I have an interaction which, as I mentioned, is something that's constant, independent of different lattice sites. And so that's actually the model in the end that we will study. This is a model that is translationally invariant and periodic. And also here I've used nearest neighbor. And this is the model that we will actually study in the following. As I mentioned, it's not the most general type of model, but it's actually extremely rich and contains a lot of physics that we'll discuss at length. And interestingly, even though we have a model here which is defined on the lattice with an infinite number of degrees of freedom, and I've not specified which particular lattice we're talking about, the actual lattice dimensionality and geometry is contained in this, basically in this term here with these angle brackets. This model actually just contains a single parameter. So we can think of a single, we can think of the physics in terms of this single parameter, which is dimensionless, which is the value of u over t. So this is basically saying the unit of energy is T, and we can measure the Coulomb interaction U in units of T. So there's just one single parameter in this model. We can look at the model on different lattices. That's true, that will give us different physics. Certainly that will give us different physics. But for a given lattice, there's only one tuning parameter, if you like, which determines what happens, and that's this ratio U over T. And U over T is the ratio between the potential energy and the kinetic energy. T is the tunneling between neighbouring sites, that's a kinetic energy. U is the Coulomb interaction, so that's potential energy. So this model captures, in essence, at its heart, the competition between kinetic and potential energies. The Hubbard model that I've written down here is, I think it is safe to say, one of the most widely studied models in all of physics. It's something that has been around for a long time. It's still many surprises, and it's still a matter of open research. It's a highly complex model containing a rich range of physics, describing many real materials. So this model is used to really describe real material systems. For example, this Hubbard model describes famously the transition metal oxides. These transition metal oxides feature the metal-insulator Mott transition, and they're also describing, or they also characterize strongly interacting lattice systems, which are so-called heavy fermion systems. The Hubbard model also describes lanthanide materials. Or a variant on the Hubbard model called the periodic Anderson model captures very well the properties of lanthanide materials, which give rise to so-called condo-insulating behavior. And these Hubbard models also, probably most importantly, describe high-temperature superconductors. For example, the perovskite materials. In particular, these high-temperature superconductors have copper oxide planes. Typically, in these perovskites at least, they have these copper oxide planes, which are basically perfect 2D square lattices, and they're described well by the Hubbard model on a 2D square lattice, a single band Hubbard model on the 2D square lattice. And it is believed that this, even this simple model, the Hubbard model on the 2D square lattice, captures the essence of high-temperature superconductivity. There's been a vast amount of work on this, and I would say the matter is still not settled. So this is the Hubbard model again on the lattice, a translationally invariant lattice. It's a simple one-band problem, and the particular lattice is parameterized, or is sort of specified. It's hidden away in this sum over nearest neighbor terms here. Why is the Hubbard model hard to solve? Well, there's no exact solutions to the Hubbard model, except in very specific cases. For example, the one-band, one-dimensional Hubbard model does admit an exact solution through the so-called beta ansatz. That's an extremely sophisticated method, well beyond the scope of this course, but just to let you know, that is in principle possible. But for the 2D Hubbard model, for example, on the square lattice, that people would really like to know the solution to, due to this connection with high TC superconductivity, there is no exact solution. Indeed, most situations that you could imagine, there is no exact solution. And one can, of course, resort to numerical exact diagonalization, but as we'll see, the system sizes are so laughably small that we can say very little from direct numerical simulations. Another possibility, of course, is to do approximations, but we'll see that this model has very rich physics in the non-perturbative regime. So if we look at a ratio U over T that's very, very small, we can do perturbation theory in the interaction strength U. If we consider U over T very, very large, we can do perturbation theory in the tunneling T. But actually, a great deal of interesting physics happens when U over T is of order 1, and that's a non-perturbative regime. So how do we treat this interesting regime? That's the regime, of course, when the potential energy and the kinetic energy are competing with each other, and we want to know what's happening in that regime. So there are no general analytic methods to solve this expression, this Hamiltonian, and there are of course, general numerical strategies, but they're confined to such small system sizes that it's hard to know what's going on. Why is that? Why is it so hard? Well, it comes from the fact that this is not a quadratic Hamiltonian. This is not a quadratic Hamiltonian, not quadratic in fermion operators. So if we have a tight binding model, we can write it in this form, where this T here is an n by n matrix of parameters for an n orbital system. And diagonalizing that is not so bad. And we can see it's an n by n matrix because if we have n orbitals in the system, then we have n creation and destruction operators, and therefore these vectors are of dimension n. However, we cannot cast the Hubbard model in such a form. And that's due to the structure of this 4 fermion term. So there's no way that I can make a canonical transformation of the operators C vector equals U F vector, for example, where I can choose the matrix U to diagonalize the matrix T. There's no way I can diagonalize the Hamiltonian operator in general because I can't write it in this special form, which comes from the fact that I have number operators featuring in the Hamiltonian and 4 fermion terms rather than just a quadratic Hamiltonian. That's the mathematical reason, and the physics reason is, of course, to be able to say whether or not I have a given interaction, I need to know simultaneously where 2 particles are. The interaction is pairwise, but I need to know where both of the particles are. So single particle states and energies are just not enough. So instead, we need to construct the Hamiltonian matrix in the many-particle basis. I mean, let's construct a matrix H in some particular basis of basis states phi. That will have elements ij, which are precisely the Hamiltonian operator sandwiched between our basis states phi I and phi j. And then we make a matrix of those matrix elements for all the different I and j, and then I form this big matrix H, and then I can diagonalize this matrix. Which basically means we need to find a matrix U such that U dagger H U is equal to a diagonal matrix. And as we showed in the previous lectures, this is completely equivalent to solving the Schrödinger equation. The rows or columns of our matrix U are the wave functions, and our diagonal elements of the matrix D are our energies. But here comes the catch. To form this Hamiltonian matrix, we need to find matrix elements between all of our basis states, the phi, which are the phi i's. So we have a set of these phi i's. How many? Well, if we have spin in the game, then each orbital can either be empty, singly occupied with an up or down spin, or doubly occupied. So it has a four-dimensional local Hilbert space. And so the basis is of dimension 4 to the power of n for n orbitals in the system. So, for example, if I have a single orbital, I have 4 degrees of freedom. If I have 2 orbitals, I have 16 degrees of freedom. And if I have 3 orbitals, I have to multiply this by another factor of 4, and I keep multiplying by a factor of 4 for every orbital that I add. And this is an exponential growth of the underlying Fock space. So when I construct my Hamiltonian matrix, and I want to diagonalize it, it becomes a matrix of dimension 4 to the n by 4 to the n. And doing the numerical diagonalization of a matrix scales as the dimension cubed, and one needs to store in memory something of the order of the matrix dimension squared. And so one very quickly runs out of computational resources. In fact, what's the largest system one can solve? Well, one can do straightforward brute force calculations for maybe 8 orbitals. If you use the state-of-the-art methods currently, maybe you can go up to something like 20 orbitals. But 20 orbitals is nothing of like what we need to understand the properties of a condensed matter system with 10 to the 23 electrons. It's nothing like what we need to understand what's going on the lattice. For example, let's say I have a 3D cubic lattice. If I have a 3 by 3 by 3 cube on this 3D cubic lattice, that's already 27 sides. That's already beyond the state of the art, and that is not really much of the lattice at all. So the curse of dimensionality, as it's called, prevents us from doing a direct brute force calculation. So we need to be much more clever to understand what's going on in these systems. So the take-home message here is that direct brute force calculations numerically in the many-particle basis are simply impossible. If you only take away one message from this lecture, I want you to understand that interacting quantum many-body systems are exponentially harder than these quadratic type-binding models. And this is a major area in condensed matter physics to study. The problem of interactions is the main problem in physics in terms of complexity. And you can't just go ahead and calculate it, not even with the fastest computers. Let's say in 50 years' time, we've increased the complexity or the abilities of our computers by 1,000 times. That's only adding a couple of extra orbitals into our system. We really need to do something completely different to understand the physics of these systems. So what is the underlying physics of the Hubbard model? The Hubbard model, as I mentioned, hosts a very rich range of different physics. For example, metallic behavior, insulating behavior, magnetism, superconductivity. If you consider different lattices, for example, frustrated lattices, it's possible to have quantum spin liquids, all sorts of interesting things. But one of the most paradigmatic features of the Hubbard model is the so-called Mott metal-insulator transition. And this is sometimes called the Mott-Hubbard transition because it's a metal-insulator transition that's driven by the interactions, and it's something that is captured already in this simple Hubbard model. The metal-insulator transition is a so-called quantum phase transition in the sense that the transition between a metal and an insulator can happen even at 0 temperature, as one of the parameters is tuned. And the parameter, for example, could be the ratio, or the parameter is, in this model, the ratio between the potential and the kinetic energy terms U over T. And in real systems, this can be tuned, for example, by applying some pressure to the system, which squeezes the atoms closer together, and this increases the tunneling amplitude T between sites. Or you could apply some chemical pressure by doping or something like that. Of course, as we move from material to material and use different atoms from the periodic table to construct our material, naturally, because of the different atoms used and the different lattice structure, different lattice constants and so on, the ratio of U and T changes. So different materials occupy different points on the phase diagram. So as we tune the ratio of U over T, we can have a transition from a metal to an insulator, even at 0 temperature. However, as we go to finite temperature, this transition persists, and so we can draw a phase diagram in the space of temperature and U over T. In fact, usually the experimental measure would be temperature and pressure. As I mentioned, as you increase the pressure, you're increasing the T, and therefore decreasing the U over T. So the experimentally accessible phase diagram would look something like this: temperature on the y-axis and pressure, which is basically a measure of T over U, on the x-axis. And we see a quantum phase transition at a particular point at 0 temperature for a particular value of T over U. And as we increase the temperature, this phase boundary moves off in this way. On the left-hand side, we have a insulator, and on the right-hand side, we have a metal. And so we actually see something rather interesting, and this is an experimentally derived phase diagram, as well as something one gets from a theoretical treatment. If one imagines sitting in the metallic phase, for example here, for a given pressure and temperature, and warming up the system, so I keep the pressure the same and I just warm the system up, then I take this cut through the phase diagram, and then I see something quite interesting happens, which is that I go from a metal to an insulator by increasing the temperature. And this is one of the weird things about the Mott transition, that there's a region of the phase diagram where increasing the temperature causes the system to become an insulator. Normally, you'd expect increasing the temperature in a band insulator would cause it to become a metal, because you're providing the electrons with more energy. There's more energy per electron. There's a thermal energy, which means they'll be able to overcome the excitation gap between the valence and the conduction bands, and that will allow them to conduct. So we see something that's actually kind of the opposite here in the Mott transition. And then at some point I've drawn this sort of phase line sort of ending, and there's some kind of crossover behavior between the metal and insulator at high temperatures. And in fact, depending on the particular lattice that's chosen and details of the system, detailed study seems to suggest that actually there is a region here which is a superconductor around this point of where the quantum phase transition would be at 0 temperature between the metal and insulator. And people have also suggested that, for example, there might be a region here which is a spin liquid behavior. We talked about that a bit when we were discussing spin systems, the first part of the course. And the metal, of course, is a so-called heavy fermion metal. So not a conventional metal either. So there's potentially lots of interesting physics happening here, even captured in this simple Hubbard model. One can also consider different types of phase diagram. For example, even at 0 temperature, one could think about the phase diagram as a function of U over T and doping. So this is basically setting the Fermi level, and one can achieve this by chemical doping, so substituting certain atoms in the lattice with other elements which have more or less electrons, and this basically changes the average filling of the bands. And what one finds in this case is that even the whole diagram now is at t equals 0, one can find that the original Mott transition occurring at 0 doping can sort of be extended out in this plane, something like this. The way I've written this with u over t on the x-axis here, it's this side that's the insulator, and this side is the metal. So this has a very rich physics in this model. It's very important to note that the Mott transition and the Hubbard model the physics of this system cannot be understood in terms of the single particle picture of non-interacting fermions described by the tight binding model, which is just the first term here in this Hamiltonian. In particular, we see that we can get insulating behavior in this model when we still have partially filled single particle bands. So from a band structure point of view, we know that if we have a partially filled band, there are low energy ways of redistributing the electrons, and we can get a current to flow by applying an electric field, and there's no energy gap in the band structure to prevent that. So partially filled bands, from a band structure, non-interacting band structure point of view, is synonymous with conducting metallic behavior. However, for the Mott insulator, we have a very different scenario. If I imagine the Hubbard model in a part of the phase diagram which corresponds to the insulator, in this Mott insulating phase, as it's called, we can still have partially filled non-interacting bands, yet insulating behavior. And this is because we need to go beyond the simple single particle picture. In particular, the idea is that if we have strong interactions, the electrons become localized on their individual lattice sites. For an electron to tunnel from one lattice site to the other means that a given lattice site might host two electrons momentarily before one of the electrons tunnels off through the lattice. So these fluctuations in the local charge are suppressed if we have strong local Coulomb repulsion. And if the Coulomb repulsion becomes large enough, it turns out that we enter a totally insulating phase. So there is a gap to excitations, but we need to consider the many-particle excitation spectrum for this. We need to consider the many-particle energies and levels. We cannot just get away with using this first term in the Hamiltonian here, which describes the non-interacting band structure. So in a very heuristic way, let's discuss physically what's happening in these two phases. Let's look at the standard Hubbard model here depicted on a 2D square lattice. And let's imagine that we have a half-filled lattice, meaning that on average there's one electron per site, and that electron can either be up or down spin. Let's first take the case of the metallic phase, where we have a small interaction strength relative to the quantum tunneling amplitude T. So what would happen in such a system? Well, the kinetic energy overwhelms the potential energy, and so we could imagine that we're happy to pay the price of the Coulomb repulsion to allow the electrons to move around and gain kinetic energy. So that's exactly what happens. We can imagine taking this spin here in the top left and quantum tunneling it to its neighbouring site, and that is that has an amplitude, a tunneling amplitude of T. And this is the resulting state, where here we now have a Coulomb interaction between these two electrons occupying the same site, which is of order U. And relative to the half-filled background of the lattice, here we have a particle-hole excitation. So here we have a hole where previously there was a particle, and here we have an extra particle relative to the background. So this is called an exciton. But of course this is not a static thing, because these particles and holes can themselves move around. For example, this downspin can quantum tunnel to this neighbouring orbital with a Hoppling amplitude of t, and it can either happen at the same time or sequentially. We could imagine that this electron hops in this direction with a tunneling amplitude of t. And so we'd arrive at a state like this. And here you can see, for example, we have this particle-hole excitation here, but there's also other interesting things going on, because relative to the antiferromagnetic Néel magnetic order that I drew at the beginning, with alternating up and down spins, here we see that there's actually a magnetic excitation as well, with two spins being parallel rather than anti-parallel. So there are different kind of excitations that can be generated from the tunneling of the electrons around on this lattice. Let's consider some more tunneling events. I can imagine these two electrons tunneling, which would give me this state, and maybe these two electrons also tunnel, which would produce this state, and so on. So we can see that over time these electrons can tunnel and produce totally different states. So this original antiferromagnetically ordered state that I drew gets completely scrambled up, and there's not really much hint of antiferromagnetism left on this lattice after just a few steps. And we see all sorts of different kinds of excitations, magnetic excitations, these excitonic particle-hole excitations, and so on. Now, the point is that in the metallic phase, when the Coulomb interaction is much less than the tunneling amplitude t, these kind of processes are favoured because it allows electrons to move around and the electrons gain kinetic energy. The penalty which one gets from these doubly occupied regions here is insufficient to suppress the itineracy of the electrons, because the dominant interaction is the tunneling, which is a kinetic term. And what we see is that this kinetic term, of course, completely scrambles all of the electrons. It gives a completely disordered state. The electrons are free to roam around, and indeed they are metallic. One could imagine applying an electric field to this system to bias the electrons to move in a particular way, and we'd get a current to flow. Of course, one should take these cartoons that I'm drawing here with a bit of a pinch of salt. This is only meant to be a cartoon. None of the states that I'm writing here are eigenstates of the system. This is a quantum mechanical system. But one can imagine that these kind of cartoon states that I've been drawing are the kind of classical terms that would enter into a linear superposition of states, which would actually be the real eigenstates of the system. Okay, so now let's consider the other limit of the insulating phase, when the Coulomb repulsion U is much, much greater than the tunneling amplitude T. And I've reset the board here. We go back to the square lattice. Again, on average, it's half filled. And again, I've sort of rather suggestively indicated Néel antiferromagnetic ordering of the spins on the lattice. That's actually not by accident. We'll talk more about why one might expect that behaviour shortly. But for now, let's just assume that we have a starting position for this board, if you like, for these antiferromagnetically anti-parallel spins arranged on the 2D square lattice, and I'm going to consider now the insulating phase with large Coulomb repulsion. The Coulomb repulsion is, of course, local, because we're talking about the Hubbard model. So the kind of things we can imagine are to take this electron here, for example, and to quantum tunnel it onto its neighbouring site. The amplitude for that event would be t, but the resulting state is a high-energy excited state, which is of order u higher than the background ground state that I've drawn here. So that excitation that I've drawn there would result in this state, in which we have a doubly occupied orbital, and that doubly occupied orbital costs an energy u, and we don't like this state. This is not a good state because the energy cost is extremely high. U is much, much greater than T. So does that mean to say that we never have such tunneling events? Well, no, of course not. This is quantum mechanics. the tunnelling event can occur, but in the phase u much greater than t, it implies that this excited state has a short lifetime. The lifetime gets shorter and shorter as the excitation energy becomes larger. So the electron should move again. It could move down here, for example, but that is again a high energy state. So in fact, the only way to return the state to its low energy configuration is for the electron to tunnel back again from here to here. But now we have two choices. We can either tunnel the upspin or the downspin. So let's say that we tunnel the downspin. So here we have a new configuration on the lattice. We've restored the condition that there's one electron on each side, not just on average, but literally one electron on each side. And therefore we're not paying any Coulomb repulsion at all over the whole lattice, because as you can see from the term in the Hamiltonian, we only pay the Coulomb term when we have two electrons occupying the same orbital, and all of the orbitals on this patch of the lattice that I've drawn are singly occupied, and therefore there's no Coulomb repulsion to pay at all. So this is obviously the low energy state. So what we see is that we can have excitations of the charge, where we see these particle hole excitations, but these are virtual excitations. They're very short-lived. The electron hops over from one side to the next, but then very quickly hops back again into its low energy configuration, because the high energy states are suppressed by the large energy gap of order U. So we do get a small amount of stabilization from the kinetic energy from these hops of the electrons to their nearest neighbors, provided that they hop back again. So by this mechanism, we see that the electrons become localized due to the strong Coulomb interaction. The electrons are not free to just move around the whole lattice. If the electrons hop to a neighbor, they have to hop back again. If I apply an electric field to this system, there are no low energy ways in order to get the electrons to move throughout the whole lattice and become itinerant. They're kind of trapped, the electrons are localized, and therefore we have an insulating phase. Even though, on the level of the one electron band structure, which is just described by this for the 2D square lattice, we know from the previous lecture that this would be a one-band problem with a partially filled band, yet the Coulomb interaction is suppressing these tunneling events and making this system an insulator. So what are the properties of this insulator? Well, actually, the insulator is magnetic. It has antiferromagnetic Néel ordering, and that's actually what I sort of presaged by the cartoon at the very beginning. And we can actually see a hint of that due to the excitation process that I just sketched out. For example, here we have two electrons that are parallel aligned because I hopped the one electron over from one side to the other, but then I hopped the opposite spin back again. That creates a parallel alignment here, a parallel alignment here, a parallel alignment here, and then also a parallel alignment with these spins. So this single process that I sketched actually has created quite a lot of parallel spins rather than anti-parallel spins. Okay, so who cares? What's wrong with that? Well, let's consider the next tunneling processes. We could imagine trying to tunnel this electron to its neighbors. And we do that by indicating this arrow here. But we can see that that cannot occur because of the Pauli principle. I can only have spin anti-parallel pairs of electrons occupying the same orbital. Likewise, I cannot hop this electron to this nearest neighbor here for the same reason. And likewise, I cannot hop this electron in any of these directions, or this one here. All of these hops on the lattice are now suppressed basically just by the Pauli principle. So what we see from this is that if I want to allow for a certain stabilization due to the kinetic energy for these virtual excitations for tunneling between nearest neighbors and back again, then I actually want a very specific kind of process to maximize the kinetic energy stabilization. I want in particular that if a spin up electron tunnels to its neighbouring site, then the same spin up tunnels back again. I don't want any spin flip excitations because this will disrupt the ability for hops on the lattice. And this is the microscopic origin, in the end, of the antiferromagnetic ordering. It's only by having anti-parallel aligned spins throughout the entire lattice that I can have these virtual excitations of these electrons hopping to their neighbours and then back again. And overall, all of that lowers the energy of the state and gives us some stabilisation. So let's reset the board again and show the kind of processes that are favoured. We imagine that we can hop or tunnel this electron from here to here. That produces this high-energy virtual state, and this has a short lifetime, and then we return back to the original configuration. We do that by hopping the upspin back again to the original site, and the antiferromagnetic order is restored, but it does mean that I can now continue to have other hops on the lattice, which are virtual excitations, but all serve to lower the overall energy. So one should not think of the insulating phase as being totally static. There are these fluctuations, but they're virtual fluctuations, and in fact it's these virtual fluctuations that give rise to the magnetic ordering on the lattice. Of course, what I've described here is a very heuristic and cartoony way. This is obviously in the real system we have superpositions, and we don't think about these classical pictures. However, there is a rigorous mathematical way of treating these things that I will describe shortly, and we'll see that basically this is the right physical picture. These are the kind of processes indeed that give rise to antiferromagnetism for the case of the insulating phase and these itinerant electrons in the metallic phase where they can move around. So let's take a look now at the density of states, or the excitation spectrum that we get in the Hubbard model. So I won't do any exact calculations here. I just simply want to argue the kind of physics that we might expect. And again, we'll resort to the two different limits. Let's consider first the extreme limiting scenario of the Coulomb interaction U goes to 0. Then we're left with the non-interacting tight binding model with electrons, for example, hopping around on a 2D square lattice. And because we just have a single orbital in the unit cell, we know that we'll have a single band, and that not all energies are accessible. All of the eigenstates exist within a finite support of energies, and so we can write down, or we can draw qualitatively what we expect the density of states to be for such a system. So let's plot here the density of states, rho, as a function of the energy E, and then in the middle here we'll put the Fermi energy, EF. And qualitatively what we'd expect is a single band, something like this, and the width of this band we can call W. If this was a square lattice, then this W, from the calculations that we did in the previous lecture, would actually be equal to 8t, where t is precisely this tunneling amplitude in the Hamiltonian. Actually, the shape of the band would look a bit different, but broadly speaking, the idea is that we have a certain finite density within a finite bandwidth, which is this W. In particular, if we want to have a half-filled system with an average occupation of each site of 1, then we just fill up the single particle states up until the Fermi energy. And if exactly half of the total number of states lie below the Fermi energy, then we have a half-filled system. We can control the occupation of our system by changing the chemical potential, and we can actually add that into our Hamiltonian. Let's write that here. an extra term minus mu, the sum over all sites, times the number operator for that site. And this will be a constant shift in the energy of the whole system, which basically defines the Fermi energy. And if we want a half-filled system, which in the limit u goes to 0, then we just need to pick mu is equal to 0, because exactly half of the total number of states lie below the Fermi energy. So when we want to fill up the Fermi C up until the Fermi energy, exactly half the states are filled, and we have half filling. So that's what we'd expect in the limit u goes to 0. And we can imagine that if we put on a small finite u, then not much would change to this picture. Let's consider another extreme limit, the extreme limit where t goes to 0. This is the so-called atomic limit, because we imagine each atom being now totally isolated from all of the neighbours. What do we expect from the density of states in such a case? We again plot the number of states per energy as a function of the energy on the x-axis, with the Fermi energy in the middle. So what would happen in such a case? Well, the system is going to be very, very highly degenerate, macroscopically degenerate, because we have n orbitals in the system, with n of order 10 to the 23, which is tending to infinity. But each of those atoms is isolated from its neighbours because the tunnelling amplitude, t, has been set to 0. So it suffices to understand the entire properties of the whole system as just a highly degenerate version of a single atom. And the single atom, the properties of the single atom, are just controlled by this Coulomb term. And so we can actually just solve that exactly for a single atom. And that is extremely simple to do, precisely because it's not a many-body problem. We have just a single atom. Okay, so let's try that. We actually also have, of course, this chemical potential term in there, so I'll include that as well. So I can imagine applying my Hamiltonian to a given basis state, u, n up, n down, for a particular state, minus mu n up plus n down. You see here I have the sum over sigma as well. That's the Hamiltonian that I'm going to be interested in this particular case. And I want to apply this to the various basis states. So, for example, I'm going to apply h to the empty state, and of course I will just get 0 because there's no electrons there. If I apply h to an upspin electron state, I will actually get minus mu as the contribution to the energy. But I don't get any term from the Coulomb repulsion because there are not 2 electrons there. Likewise, h acting on the down state give me minus mu. But h acting on the doubly occupied state, there are 2 electrons there, so I get minus 2 mu plus the Coulomb interaction u, which penalizes the double occupation. So relative to the half-filled ground state, we can have a whole excitation where we remove an electron, and that would be sitting somewhere here at an energy of minus mu. And we can also have a particle excitation where we add an electron to the half-filled ground state, and that would be some excitation energy over here with an energy of u minus 2 mu. And provided we have that mu is greater than 0 but less than mu, then we'll have an exactly half-filled system, because we'll have one excitation below the Fermi energy and one excitation above the Fermi energy. So this is the situation in the extreme atomic limit scenario where the tunneling between sites goes to zero, I could imagine switching on a very small finite tunneling between orbitals, but keeping the U as the largest energy scale in the problem by far. And what will happen then is these poles in the density become broadened. So instead of having perfectly localized states, the electrons can start to move around a little bit on the lattice. They gain a bit of dispersion. These poles become a bit broadened, and so with finite t, these poles turn into peaks. But those things are basically separated by an energy gap of order the interaction strength U. And that's the important point. So this would be an insulator, as you can see, because there's an energy gap of order the Coulomb interaction. For finite t, there is some finite broadening here of order W. That's the width of these bands. That's basically related to t. And what you can see is that when U and W become of the same order, this gap kind of closes, and one could imagine crossing over from the insulator to the metal. So all of this is certainly beyond any kind of perturbative approach when U and V are of the same order, but at least from this cartoon sketch here, we can understand these two extreme limits. And in fact, a full treatment of the model yields something like this. When we have U equals naught, we have the simple non-interacting band structure for whatever lattice we're talking about. We have a single band which is partially filled. As we jack up the interaction strength, we see things start to change a little bit, but we still have a partially filled single band, which is still metallic. In the extreme limits of large U, we have two separated bands. The bands are separated by the interaction strength. But the interesting thing, of course, is this intermediate regime, where we do see some features of both limiting scenarios. On the one hand, we see a very narrow quasi-particle resonance around the Fermi energy, so we still have a metal here, but then we start to see this sort of preformed gap emerging, separated from these two flanking Hubbard bands, as they're called. So this is the full solution of this is numerically very demanding. There are very few analytic methods that can give such a beautiful description as this, and that's beyond the scope of this course, but this is certainly the phenomenology, both from the theory side and also from experiment. So what I want to talk about now is the Stoner model of itinerant or metallic ferromagnetism. Previously, we discussed magnetism in the context of the Heisenberg model and of spin models, but in those models we assume that the spins are pinned and localized to particular lattice sites, and the electrons are not moving around. So when we discussed the insulating phase of the Hubbard model a few slides ago, we saw that we can have magnetic states, but it looked like on the metallic side that we have a disordered situation with no magnetism. And yet we actually know, of course, from nature that we can have metals, for example iron, which are both conductors and also have ferromagnetism. So contained within the Hubbard model, the solutions of the Hubbard model, is apparently this phenomenon of metallic or itinerant ferromagnetism. So can we take the Hubbard model and understand what's going on there on the metallic side? I'll argue that the Hubbard model is sufficient because the short-range part of the Coulomb interaction is the dominant part, and what we'll have here is to include both the strong interactions of the electrons in narrow and localized d or f orbitals of the heavier transition metals, for example, but also we need to include the quantum tunneling of electrons throughout the lattice if they're to be metals. So the Hubbard model is the right place to start. However, we want to think of a simple explanation for itinerant ferromagnetism. We don't have many exact solutions at our fingertips except for the simplest possible cases. And so what we'd like is a simple mean field treatment of this Hamiltonian, the so-called Hartree-Fock approximation. And the first step is to apply the Fourier transform to this Hamiltonian. If we didn't have the Coulomb term, this would totally diagonalize the Hamiltonian, and we'd end up with these single particle levels. However, because we have this additional term sitting here, that messes it up, and it won't be fully diagonal. But the first step is to go to momentum space. If we just had the tight binding term in our Hamiltonian, then we'd just obtain this completely diagonalized piece. But of course, the story doesn't end there, because we also get a contribution from the Coulomb interaction, which gets completely scrambled in the momentum space basis. If you imagine doing the Fourier transform of the C operators, and here we have a 4 fermion term, the term we'll generate will be something of order u over n squared, where n is the number of orbitals in the system. And then I have an enormous sum over momenta for each of the operators, k1, k2, k3, and k4. And then the operators in question will be C, k1 up, dagger, C, k2 up, C, k3 down, dagger, C, k4 down. So this is the transformation of the Hubbard term. But if we imagine a diagram corresponding to this interaction, we'd have something like this. We have an ingoing state, k1 up, that gets scattered into an outgoing state, k2 up, and it does that because of this interaction u, in which on the right hand side we have a state k3 down being scattered into k4 down. And that's all fine. We have conservation of charge and we have conservation of spin. But if we were to also have conservation of momentum at the vertices of the interaction, then we should have that k1 plus k3 is equal to k2 plus k4. And we can write that in a simple way. We can say that k2 is equal to k1 plus some momentum transfer q, provided that k4 loses that same amount of momentum. So k4 is equal to k3 minus q. And so using this conservation of momentum rule, we can rewrite this expression and collapse one of the sums, and we'll just write it as k, k primed, and q. And now what we see in this expression is c of k plus q with an upspin, dagger, c k up, and then c k primed minus q down, dagger, c k primed down. So now we're going to use the mean field or Hartree-Fock approximation to treat this complicated term. And this is very much in the spirit of other mean field theories that we've talked about in this lecture course. The idea is that we're going to treat each electron in the system as if it sees an averaged interaction from all of the other electrons in the system, rather than taking into account each individual interaction separately. And then with this averaged interaction, we'll assume that that same averaged interaction applies to all electrons in the system, and therefore we'll have a self-consistency equation. So in practice, we're going to treat this 4 fermion term here, which appears in our Hamiltonian, and we're going to factorize it in terms of pieces with averages and pieces with operators. And the trick to the Hartree-Fock approximation is to consider all possible combinations subject to charge and spin conservation. So all possible combinations of operators where we have operators and averages, and we're going to split this up into quadratic pieces. So for example, let's keep the first two operators, but consider the average of the second two operators. That's one possible mean field decomposition, but of course that's not the only one, and we want to consider all possible combinations. For example, this is an alternative decomposition, but that's not the only one. We also have these factorizations, but notice here we have these minus signs, and that's coming because I had to reorder these operators, and when I do that I have to take account of the anti-commutation relations. And finally, I can include terms where everything is averaged over. And we get these terms if we just average over pairs of operators in the spirit of the usual mean field approximation. So to make progress with this, we use the Hartree-Fock approximation, which is, first of all, that there is no amplitude for scattering of a down state to an up state with any momentum. And that's just because in the original model we had overall spin conservation. So these averages would actually be zero in the original model. And furthermore, we'll assume that the scattering is on shell, meaning that we only consider the pieces diagonal in K1 and K2. However, as you can see from here, we do allow the average population of the K1 upspin orbital to be different from the average occupation of the K1 down orbital. And this is precisely what we're trying to achieve. We want to be able to describe the phenomenon of ferromagnetism, which means we want to allow the expectation values of the populations to depend on the direction of the spin. So here, explicitly, I'm allowing for this symmetry breaking, and we'll see that the solutions, the self-consistent solutions, actually can become spontaneously symmetry broken. This symmetry breaking is not a symmetry of the original model, but we allow for it within mean field theory, and we see that indeed these broken symmetry states are the preferred thermodynamic phase. Furthermore, we can consider the momentum summed occupation, which I'll call n up, the average of n up, and this is going to be just the sum over all momenta of the n k up object, and likewise the average of n down, that's the overall average summed over k and divided by the number of states, will just be the average of nk down. We can now substitute that into our mean field Hamiltonian, and we would get the following, which basically tells us that the population of the k up orbital depends on the average value of the occupation of the down electrons in the entire system, and the population of a given k down orbital depends on the average n up population in the whole system. Plus, there's a constant added to the Hamiltonian here that doesn't affect the dynamics, so we'll ignore that in what follows. So we can write this whole thing in a nice, simple, quadratic form. Which is now in the form of a free electron gas, where the free electron gas dispersion is given by epsilon k up is equal to the free electron part epsilon k plus u times n down average, the average population of the opposite spin species, whereas epsilon k down is of course just equal to epsilon k plus u n up average. And so we can analyze this problem now in terms of just a free electron gas. Now we can understand the solutions to this problem by writing down a self-consistency equation, And we can do that because the Hamiltonian features the average occupation number of a given spin species. But of course, the average occupation number of a given spin species is something that should come out of the Hamiltonian after we look at the statistical mechanics of that system. So the thing that we put into the Hamiltonian should be the thing that we get out from the Hamiltonian, and that leads to a kind of closed-loop consistency equation. So here I've just written down from statistical mechanics what the average occupation of a given spin species should be in our system if our system is a free electron gas, which we've written it down in the form of. And that's related, of course, just to the Fermi-Dirac distribution. So this is something that we can just calculate. In particular, if we know the dispersion relation for the tight binding part of the model, then this is something we can just work out. However, let's make a few approximations and make some analytic progress using the well-known properties of the electron gas. In particular, let's connect the occupation number to the Fermi wave number. We have this famous relation where Kf here is the Fermi wave number. And the Fermi wave number of the system is, of course, related to the chemical potential. We just take the kinetic energy part, but in this system, we have a different chemical potential for the up and down spins. So here I should really write mu of sigma, where mu of sigma is the original mu that we put into the model, the original chemical potential, minus now this shift, which is exactly U times N sigma bar. So sigma bar is the opposite spin species to sigma. So combining these equations, we simply get, in terms of the population of the up and down spins and the overall chemical potential of the system. So this is valid for the free electron gas. And with a little algebraic magic, we can solve these equations. Let's introduce these auxiliary variables. Then, with a bit of manipulation, it can be shown that we have this equation in terms of these auxiliary variables, and we just get that by substituting in and manipulating a little bit these two expressions into these expressions, the self-consistency expressions for the spin populations. In particular, notice that this psi object here tells us about the polarization in the system. It's the relative polarization. It tells you about the difference in the spin species normalized by the total density. Whereas this gamma parameter here tells us about the relative strength of the interactions in the system in terms of also the total density of the system. We might expect that as gamma increases due to increasing interaction strength, then we'll be able to get a polarized state, because of course it's the interactions that are driving the ferromagnetism in this system. And of course that's exactly what we find in the exact solution of this equation. It has different regimes. Let's consider them. First of all, we have a normal unmagnetized state with psi equals 0. This is the isotropic solution, and it's obtained for any gamma less than 4/3. So this is telling you that for weak interactions there is no ferromagnetism in this system. So if we were to plot the density of states here as a function of energy, we would see that for the up and down spin species, we have basically the same density of states. We have the same spin populations for up and down spin, therefore the psi is equal to 0. However, it is also possible to have solutions with partial polarization with a psi between 0 and 1. So this tells you that there's an imbalance in the average populations of up and down spin species, normalized by the total density. And this gives rise to essentially a weak ferromagnet. And that's obtained for a gamma parameter, which is between 4/3 and this interesting number 2 to the 2/3. So that's telling you that as you increase the interactions beyond this value of gamma equals 4/3, you enter a regime with the polarization steadily increasing. And the corresponding density of states picture will look like something like this. So for a given chemical potential, we see an imbalance between the populations of the up and the down spin. We have a much greater number of upspins than downspins because the downspin band has been moved up in energy relative to the upspin. And finally, of course, you can see that it's possible to have a full polarization, psi equals 1. This is a strong ferromagnet. Which is obtained for strong interactions gamma greater than 2 to the 2/3. And the density of states picture then looks like this, where now the entire down electron band has been pushed above the Fermi energy and therefore is totally unoccupied. It's only the upspin band that becomes partially occupied, and so we have a full polarization. And these are the kind of physics that are contained within the Hubbard model when treated within the Hartree-Fock mean field theory. We're allowed to have a metal on the one hand, which is also spin polarized to give ferromagnetism. And this Stoner model gives a reasonable account of metallic magnets. So the possibility for getting a magnetic solution here can be traced back to the spin-dependent energies. So obviously the mean field energy of a given spin direction depends on the occupation of the opposite spin direction, whereas it does not depend on the occupation of the same spin direction. And of course, this results from the fact that the interaction in the Hubbard model is very short-ranged. Only the spins with only opposite spins occupying the same orbital interact. If you have spins with two electrons with the same spin, they do not interact with each other because the Coulomb interaction is taken to be short range, and by the Pauli principle, only opposite spin electrons can occupy the same orbital. So this leaves the interactions between opposite spins as the only possibility. And the interaction energy is lowered by having a polarized ground state, which, on the other hand, for a fixed density, costs kinetic energy. So it's really the competition between potential and kinetic energy contributions that gives rise to the phase transition here. The last topic that I want to talk about in this lecture is deriving the Heisenberg spin model from the more microscopic Hubbard model. The Hubbard model, of course, allows electrons not only to feel interactions locally when on site, but also allows them to tunnel to their neighbours. The Heisenberg model, by contrast, involves localized spins sitting on the lattice sites, and those spins are not moving around. So actually, it turns out that the Heisenberg model can be derived rigorously from the Hubbard model in the large U limit, the limit of large interaction strength. So that's what I want to talk about now. I'll first of all motivate the basic idea and argue that the emerging exchange interaction in the Heisenberg model, when derived from the Hubbard model, is antiferromagnetic, favouring antiparallel ordering of the spins. And then we'll actually do a proper perturbative calculation, which will result in a full derivation. So let's get started. First of all, I want to consider the U much greater than T limit of the Hubbard model. And I want to do this such that each site is basically occupied by a single electron. So what I want is to consider the average occupation of a given site I is basically 1. It can fluctuate a little bit, but I don't want much double occupation. So remember, of course, that if the average occupation is equal to 1, that can still include in the ensemble significant charge fluctuations to the empty or doubly occupied state, so long as the average is 1. But this additional constraint here, that the double occupation is close to 0, basically implies that we have a localized spin on each site. And that spin, of course, is sigma is either up or down, because we have spin-half electronic particles here. So what we want to do is derive an effective model which involves just the spin degrees of freedom rather than including also charge fluctuations on each site. We want to derive that rigorously from the Hubbard model, and we'll see that that effective model is the Heisenberg model. And the way this is done in practice, technically, is to do perturbation theory in the tunneling. So our T over U is our small parameter in which we'll do perturbation theory. So first of all, let's break down our Hamiltonian, our bare microscopic Hamiltonian, into a piece H0 and a piece H1. And here H1 will be the perturbation. We'll want to be able to control the filling of this system, of course, because we want each site to be occupied by a single electron, so we want a half-filled system. So we're going to need to include the chemical potential here, and we also want to include, of course, the strong Coulomb interaction. And both of those two terms are part of H0. H1 is our perturbation, which will be controlled in the small parameter t. Of course, we want to think of a dimensionless quantity that's small, that's t over u. And this is going to involve the tunneling term between our neighbouring sites on the lattice, and we have a sum over spin sigma. Write the two Hermitian conjugate terms here. So we're going to be doing perturbation theory in this H1, and in the limit that T over U is a small parameter. So this is a lattice model. It exists on some given lattice, which is basically described or hidden away inside this sum over nearest neighbours I and j that encodes the geometry and dimensionality of the lattice. But actually, we don't need to treat the entire lattice if we're just doing second-order perturbation theory, which is what we're going to be doing here. And so for simplicity, I'm actually going to just consider a two-site lattice, a very simple, simplified model. It's actually enough to see what's going on in this system, and that's why we'll do it. Once we know the result for two sites, to second-order perturbation theory at least, we'll be able to extend it to the entire lattice. So this two-site lattice that I've put in inverted commas here involves just two orbitals. There's a tunneling T between them, and then there's a local interaction U on each of the two orbitals. And of course, there's an overall chemical potential acting on the whole system, which allows you to shift the energies. So I want half filling, which in this case, of course, just means n equals 2 electrons in the two-site system. And that tells you that what I want, therefore, is a chemical potential mu that is greater than 0, but less than the Coulomb interaction U. This will trap us in the regime with 2 electrons. So the n equals 0, 1, 3, and 4 electron states are excited states. of order u above the ground state. However, even within the 2-electron sector, we have a manifold of different types of states, and what we're interested in are the spin states, the ones where each orbital of this two-site system has a single electron in it. So even though the individual occupation of each orbital is not a good quantum number, only the total filling of the entire system, capital N, is a good quantum number. But nevertheless, we want to project into a regime where each orbital is singly occupied. This is the spin manifold that we want in the Heisenberg model. So we're actually not going to consider n equals 0, 1, 3, or 4. We're just going to stay within the n equals 2 sector. This is something that I insisted upon from the beginning here. We want a half-filled system. But even within the n equals 2 sector, we see that there are different kinds of states. In particular, we have the n equals 2 ground states. They are a manifold of states in the occupation basis that look like this. There are 4 of them, and all of these have the same ground state energy of minus 2 mu. And then we have the n equals 2 excited states. The n equals 2 excited states involve charge fluctuations where one of the electrons quantum tunnels to the other side, thus meaning that we have a 0-2 or 2-0 kind of occupation. These are the excited states, and they have an energy minus 2 mu plus the Coulomb repulsion U. So you see that there's a difference in energy between the ground and excited states, could call that delta E, which is precisely the Coulomb repulsion U. So what we're interested in is the large U limit, where this gap becomes large compared to any stabilization one could get from tunneling electrons. Let's now write down a projector. Actually, it's the identity operator, which acts in the n equals 2 subspace. I will decompose that into 2 projectors, which I'll just call P and Q. Again, these are still, of course, in the n equals 2 subspace. P will be a projector onto the ground states. So we have something like this, which spans all of the possible states within the ground manifold. You can see now why I just want to do this for a 2-particle system in 2 orbitals, because it rapidly becomes more complicated otherwise. And Q, of course, is going to be the excited states. And overall, therefore, when I add P to Q, I have a complete set of states, or complete set of projectors, over all of the states in the system, and indeed that is the identity operator. I'm allowed to label the identity operator by the total filling of the system, because the total filling of the system, capital N, is a good quantum number, and so overall the Hamiltonian is block diagonal in capital N. We're just going to consider the capital N equals 2 subspace throughout this calculation. I want to consider the situation of half filling. So again, P hat is a projector onto the n equals 2 ground states, while Q projects onto the n equals 2 excited states. And as I mentioned, because the Hamiltonian commutes with the total charge n hat, we can say that the Hamiltonian conserves the total charge, and therefore we can solve the Schrödinger equation separately for each n. And in particular, we're interested in solving it within the n equals 2 sector. So within the n equals 2 sector, what does this Schrödinger equation look like? Let's imagine that we have a wave function of the entire two-site system labelled with n equals 2 electrons. That is, of course, equal to p plus q acting on this wave function, and that is because p plus q is the identity operator. But let me split that up. Let's act with p on the wave function psi, and with q acting on the wave function psi. And let me call the resulting objects phi gs for ground state and phi ex for excited state, where, just to be completely crystal clear, I'm talking about p acting on the full wave function is equal to phi gs, whereas q acting on the full wave function is equal to phi excited. So they're just the definitions of these phis that I'm going to be using, and it's written in terms of the full wave function of the system psi, and in terms of these projectors p and q, which are projectors in the n equals 2 space onto respectively the ground state and the excited state. So what do we do with this? Well, let's apply them to the Schrödinger equation. The Schrödinger equation is h psi is e psi for this wave function that I wrote down. And if I act on this entire equation with p hat, and noting that the energy, of course, is just a number and commutes with the operator p hat, then I get this. And now I can insert the identity operator here. I'm allowed to do that because inserting the identity does nothing. That's the whole point, it's the identity. And that gives me p times h times p plus q. The identity involves both p and q. On the right hand side, I won't bother to insert the identity. It's equal to 1, so I can insert it or not insert it as I please, and I don't choose to on the right hand side. So let's expand this out. On the left hand side, I get p h p acting on the wave function psi plus p h q acting on psi, and we know this gives us e times p acting on psi on the right hand side. Now notice that because I have a projector here onto part of the entire Fock space, that if I take p and I act with another projector p, it just projects onto the same space. So p times p is just equal to p. And likewise, q times q is just equal to q. So these are involutory or idempotent operators. When I act with them twice, I just get the same thing back again. Also notice, of course, that because they're orthogonal spaces, that pq is equal to qp is equal to 0. So because of that, I can just insert another p in here, and I can insert another q in here. And that doesn't do anything to the mathematical structure of the equation, but it does allow us to rewrite things slightly, because now I can write that p acting on psi is phi ground state, and q acting on psi is phi excited, and therefore I'll end up with this: p, h, p, acting on phi gs plus p hq acting on phi excited is equal to E times phi ground state. So this is somehow interesting, and we can actually do something very similar if we start from the Q expression. So let me just label this equation star. Let's quickly do the same thing starting from Q H psi. So over here we started from the Schrödinger equation, we pre-multiplied both sides by P. Now I'm just going to do the same thing pre-multiplying by Q. On the right hand side I therefore have Q acting on psi, and I just play exactly the same game, and what I will obtain is Q H Q acting this time on phi excited plus Q H P acting on phi ground is equal to E times phi excited. So I'll call that equation hash. Okay, there's actually another simplification we can make here, because H is equal to H naught plus H1, and that means that if I were to consider the combination P, H, P, this is of course equal to P, H naught, P, plus P, H1, P, but this second term here is equal to 0 because if I imagine starting off with one of the ground states contained within P, and then I act on it with H1, H1 is the tunneling term, and so that's going to give us one of the excited states. So an electron is going to tunnel from one side to the other and give an empty orbital on one side and a doubly occupied orbital on the other. So that's an excited state. But then I act again with the projector P onto the ground state, and I have an excited state, and I project onto the ground state, I get 0. Similarly, we can show that if I were to start with Q, H, Q, I get Q, H naught, Q plus Q, H1, Q. Then I start off with an excited state. If I act on it with H naught, I will remain in the excited state, whereas if I have an excited state and I act on it with H1, I'll actually go back to the ground state. But then if I project on with Q, I again kill that term. What else can we learn? Well, very similarly, we can see that if I have P, H, Q, this is actually equal in the end to P, H1, Q, and Q, H, P is equal to Q, H1, P. It's exactly the same line of argumentation. H1 is the tunneling term that connects P to Q. So if I want to go from P to Q or Q to P, I have to do that with H1, not H naught. On the other hand, if I want to stay within a given manifold, either P to P or Q to Q, then I have to act with H naught. So this allows us to actually make some simplifications in our equations star and hash. I can actually just add a 0 subscript here, and a 1 subscript here, and a 0 subscript here, and a 1 subscript here. So this is a simplification, but it's exact, there's no approximations made here, and it allows us to separate the full H into contributions H0 and the perturbation H1. Okay, so what can I do with all of this information? Well, let's have a closer look at equation hash here. what I can do is rewrite this equation so that it tells me what phi excited is in terms of phi ground. I can do that because I see phi excited on both sides of the equation. So let me just rewrite equation hash in a slightly different way. So what I have done here is just to write phi excited in terms of phi ground, and it involves this combination of operators, where in the end I had to divide through by this quantity E minus Q H naught Q, which, by the way, is called the resolvent. Okay, what can I do with this? Well, what I can actually do is plug this expression for phi excited into equation star and eliminate thereby all reference to the excited states. So I'm going to write equation star again, but I'm going to eliminate from it phi excited using this expression, and I'll obtain the following. I get term P H naught P from the original expression plus P H1 Q times this resolvent so we get something that looks pretty messy. And on the right-hand side, we simply get E times phi ground state. And this is extremely interesting because this is completely exact. There's no approximations here at all. So what we managed to do here is totally eliminate phi excited. And what we're left with is something that looks like a Schrödinger equation just for the ground state part of the wave function. So we can call all of this stuff some effective Hamiltonian. This is a bunch of operators involving H0 and H1. I just call all of that H effective, such that we have an effective Schrödinger equation which just acts on the ground state part of the wave function, which is a very interesting expression. It's an effective Schrödinger equation for the singly occupied ground state. And we have an exact expression for H effective. Now, there's a slight problem with this Schrödinger equation, which we've sort of swept under the rug by just labelling all of this thing H effective, and that is that there's the exact full wave function energy E sitting here. If we go back to the original expression, the full Schrödinger equation involves H psi equals E psi. We're now just looking at the ground state singly occupied spin manifold part of the full psi, but this E is still the exact full energy of the ground state. And indeed, this E also features on the left-hand side of the equation. So this is like a self-consistent equation where the energy, the full energy of the system, actually appears on both sides of the equation. So this expression, as I've written it down here, is not actually tractable in itself as it stands, because the exact energy is on both sides of the equation. However, what we can do is now organise this information in a power series involving H1. So this expression that I've written down here is exact, it's formally exact. What I can do, though, is expand this expression, this Schrödinger equation now, in powers of H1. And I can organise the information in that way sensibly if T over U is a small parameter. Why is that? Because this H1 is has a parameter T in it. It's controlled, the magnitude of it is controlled by the size of the tunnelling T. And in here, we have the energy difference between the full ground state and the excited states. And that's delta E. and that we earlier worked out was basically the Coulomb repulsion U. Why is this the excited state? Because I project onto the excited states, I measure the energy of the system without the perturbation, which is just U higher in energy than the single particle ground state. Now the issue, as I mentioned, is that this E here is the full energy of the system. So we have like a recursive equation where I would have to plug this back into itself multiple times. So in practice, what we do is we take this expression involving H effective. That H effective is equivalent to this full energy E. So we just plug H effective into here as an operator, which would act on this to give back the total energy. And then I have something that has a more complicated expression with some nested operators, but this E doesn't go away. I still have the E then one layer down, and then I substitute it in again and again and again, and I can do that infinitely many times. And that's just going to generate more and more of these terms involving H1. So then I just reorganize this series in powers of H1. What does that then look like? It looks like the following. I can write H effective in terms of a 0th order piece, which is just this first term, and then the next order up is actually second order in H1, and that's going to look like P H1 Q E naught this time minus Q H naught Q inverse Q H1 P, and this is the second order term. And then I have higher terms which look similar in structure but ever more complicated. Yes. So I get multiple factors of this resolvent. And of course all higher order terms. This one that I've written down here is a third order term. Actually, you can argue in this particular case that all the odd orders vanish, so I'll leave you to have a little think about that. But certainly the 0th order and the second order are finite, and they're actually the ones that we can compute and will do so fairly straightforwardly. First of all, what is this pH0 P term here? This 0th order term? Well, we start with the ground state, and we act on it with the ground state Hamiltonian, and of course we get the ground state energy. So that actually is the definition of this E0. That's actually why we pick up this E0 here in this expression, because we substitute this whole thing back into itself, and the 0th order term ends up in here, which gives me this E0. So what I've actually done here is to derive from first principles the perturbation theory itself. I've shown you here how, starting from the basic ideas of the Schrödinger equation and separating out contributions to the Hamiltonian, we can derive an expression for an effective Hamiltonian. So this is actually a derivation of what's called Brillouin-Wigner perturbation theory, and it allows us to derive very nicely these effective Hamiltonians by this string of operators. So what we want to do now is, for the problem of the Hubbard model, to actually compute this second order term and then see what effective model we get. This string of operators here might look a little bit daunting, but actually, because it's a fairly simple system with just two orbitals, it turns out this is not so difficult at all. So let's have a look at that now. So this is the term written out again. I actually dropped in here, sandwiching this H0 between these Q's, And that's because I already have this projector onto the excited subspace here, so I don't need to put them again around this H0. And indeed on the other side, I again also have the Q there. So I don't actually need to sandwich that H0 around those Qs. Okay, so we take this expression, and we have to consider all of the different possibilities within this projector P for our ground state. What I actually am going to do, for simplicity, is just consider the spin flip term in here. And what I mean by that is I'm going to imagine that the starting condition is going to be up-down, and the finishing condition is going to be down-up. So I'm going to consider explicitly this term here, where on the right-hand side I start with an up-down state, but on the left-hand side I'm going to end up with a down-up state. So overall, the spins on the two orbitals have been flipped, and this is basically part of the exchange interaction that we're seeking to understand. So this is just one of the many zoo of terms that we see in here, because there are 4 different states in this P, and there are 4 different states in this P, so there are overall 16 different ways of connecting them all. But let's just focus on this one, and then we'll see what that teaches us. Let's just remind ourselves what H1 actually is. Here it is written out in full for this 2-site system. We have the tunnelling of an upspin electron either way from 1 to 2 or 2 to 1, and the tunnelling of a downspin electron from 1 to 2 or 2 to 1. And so if I apply H1 to the state up, down, then I get 2 contributions, T lots of the 0, 2 state, plus T lots of the 2, 0 state. And notice, of course, that Q acting on this state gives us the state back again, because they're both excited states. So far we've got this far in our expression. Then I need to divide by the energy difference between the excited states, evaluated in H0, and the ground state, evaluated in H0. And we know the difference in energy there is U. Or actually, I should say that it's minus U, because it's E0 minus H0, and H0 is excited. And so we have this expression. And so, as you can see, we're slowly working our way from right to left down in this expression. Good. Now I come along again and apply the Q operator, but that's fine, because they're still excited states, so I can actually add the Q operator here, and that doesn't do anything because these are still excited states. Calculating this resolvent here didn't make me leave that that excited manifold, rather. There's one step left, which is to apply H1 again. That's basically this object, and here we have to have a tunneling of electrons contained within this H1 operator acting on these 2 basis states. So what do we get? Well, I get these 4 terms. 2 of them are equal to the other 2. So these pair of terms here came from applying H1 to this term, and these pair of terms here came from applying H1 to this term. And if you're interested to know why there are minus signs here, that's something for you to think about yourselves. Basically, it's coming from the fermionic anti-commutation relations and the way we define our basis states. So we do get some minus signs here which you need to worry about, and that's important. They need to go in to get the right algebra. Okay, so we can actually pair these 2 up. This one is the same as this one. They have the same sign. This one's the same as this one. They have the same sign. So we get some particular state. Now, we're going to close this thing off by looking at the bra here for the down-up state, and the down-up states are precisely these ones. And so, in the end, I can write that down-up H1 Q E0 minus H0 inverse QH1 of the up-down, that is a particular matrix element. All of this stuff is a matrix element. It's just a number in the end, and we've actually calculated what number it is. And we get 2t squared over u. Now the order of this term is very important. It's t squared over u because we applied the perturbation twice. H1 appeared twice here, so we get 2 powers of t. And we divide by u because that's the energy difference between the ground and the excited states. So overall, the perturbation theory is controlled in powers of t squared, or t over u, and here the second order correction is t squared over u. Overall, the Hamiltonian, of course, has units of energy, so it's t squared over u is still has dimensions of energy. So we imagine an electron hopping from one orbital to the other, and then hopping back again. That requires 2 powers of t, and the virtual excited state is u higher in energy, and that goes downstairs on the denominator. Okay, so how does this help us understand what the effective Hamiltonian is? Well, so far we've calculated this matrix element, and that matrix element sits here as one of the many terms within our effective Hamiltonian. And so now we're actually in a position to write this thing that we started with here is actually equal to 2t squared over u times an operator which is built out of these projectors. And we know from our study of spin systems that this operator is a very specific kind of thing. It lowers the spin on orbital number 1, and it raises the spin on orbital number 2. We can actually write that in spin operator language. It's S1 minus S2 plus. So we can actually write this effective model in spin operator language. Now, of course, we should work through all of the other terms in here corresponding to the different parts of P on the right-hand side and different parts of P on the left-hand side. However, you can do that, of course. Maybe you should try it as an exercise. But there's a cheats way of not bothering with this, which is basically to say that we know the underlying system has an SU2 spin symmetry, and therefore if I know one of the terms, like this one, then I can basically write down all of the terms, because I know that all of those terms are just related by rotations in spin space. In particular, I know that an exchange Hamiltonian, which has terms in it like this, which is SU2 symmetric, has a special kind of form. And if we write down an exchange type Hamiltonian of this form, JS1.S2, we can write that in terms of the z components of the spin and the raising and lowering operators like this. And we recognise that the term that we have here is precisely this one. S1 minus S2 plus is precisely this one. And that, in our exchange Hamiltonian, comes with a factor of 1/2 j. And if you were to work out all the other terms, you'd find out that the other terms matched in precisely the right ratios. We'd see an S1 plus S2 minus term with the same coefficient, and we'd find these z components with twice the coefficient. And so actually it allows us to just write down the j, and the j, of course, is 4t squared over u. So that's it. What we did here was to derive perturbation theory for this system from scratch. This is basically Brillouin-Wigner perturbation theory. Then we actually carried it out to second order. We derived an effective Hamiltonian, which we can see involves these spin raising and lowering terms. And not only that, but we actually worked out the magnitude of the exchange coupling, which is of order t squared over u, as expected. The actual number is 4t squared over u, and very importantly, this is positive, which means it's antiferromagnetic. It favours anti-parallel alignment of the spins. So from the Hubbard model, we see that the insulating phase, the Mott insulating phase, which is the one at large U, where we expect the electrons to become localized, favours magnetism, The type of magnetism it favours is the Néel kind of antiferromagnetic ordering with antiparallel spins. So what we did here was just, of course, for two orbitals, but one can extend this to the lattice, and because the interactions here are pairwise, and because we're only considering second-order perturbation theory, what one finds is that when one starts with the Hubbard model on a particular lattice, in the large T over U limit, we can project down to the Heisenberg model, which just involves these nearest neighbour exchange couplings between the spins on different sites. Okay, so that's the end of the lecture. We studied quite a lot of different things in this lecture. We talked about interacting fermionic many-body systems. These are some of the hardest problems in all of physics. We looked at simple models, we looked at simple approximations. We saw, for example, the Stoner model of itinerant ferromagnetism. We also looked at the mapping of the Hubbard model to the Heisenberg model by deriving a perturbative approach and then carrying out that perturbation theory to second order. We talked a lot about the Hubbard model, which involves a short-range version of the Coulomb interaction, which is local on each site and corresponds to a strong repulsion between opposite spins occupying the same orbital. This Hubbard model we saw is very rich and indeed captures the basic physics of the Mott metal-insulator transition, where we can see that for small U over T we have basically a metal, and then even at zero temperature we can have a transition to an insulating state where the electrons become localized, not because of the band structure, the single particle band structure, but rather because of the interactions themselves. So this is just a very short introduction to the world of strongly correlated electrons. There are many fascinating things to learn here, but that's beyond the scope of this particular course. Okay, so that's the end of this lecture. Join me next time when we'll be talking about topological quantum matter.